I'm Dr. Karl, coming to you from the lands of the Gadigal people of the Eora Nation. I acknowledge Aboriginal and Torres Strait Islander peoples as the first Australians and traditional custodians of the lands where we live, learn and work. G'day, Dr. Karl, Shadows of Science, University of Sydney, here with somebody who's not from the University of Sydney, Marcus Chown, an ex-astronomer who has written this series of books. You have opened my mind up about black holes, where after a long time I thought I was able to wrap my head around it. Now you've written this wonderful book called,
It's called A Crack in Everything.
A Crack in Everything. Where does that phrase come from?
A phrase from a poem by Leonard Cohen, the Canadian songwriter.
Got 10 chapters. Impossible Thing Before Breakfast and Quantum Stars Are Not Enough, Spinning Around, Hole in the Sky. So many of the chapters are tied to achievements or thinking of one person plus a bunch of people around them, maybe. And then you go into, hey, Hubble works out that black holes are real. Thank you very much, Hubble Space Telescope. And then you finish off philosophically with A Crack in Everything, Chapter 9, and Masters of the Universe. So where should we start?
Well, as you just identified, my book is really about people, the people who made discoveries. And it's a story of how black holes have come in from the cold. So in just over a century ago, they were considered to be so ridiculous as to not even be the preserve of science fiction. I mean, Einstein, whose theory of gravity predicts the existence of black holes, never believed in them. But gradually, over the decades, they come more and more into the centre of science until we now know that they play some key but completely puzzling role in creating the universe we see around us and in me and you having this conversation.
I'm trying to be obsessive and listen to every word you say. And black holes, so the nearest one I can think of is the big one at the centre of our galaxy, about 4 million solar masses. You're saying that is part of the reason that you and I humans can exist? And this is before we dive into the fact that black holes have no size.
Let's define black holes. So black holes are regions of space where gravity is so strong that nothing, even light, can escape. So that's why they're black.
Okay, and they have zero size. The actual singularity itself has zero size. The event horizon, which is where the escape velocity is the speed of light, has a size, I think, for the sun is 3 kilometres, and then it's just linear, a million times that, a million times the diameter. But,
exactly.
So let me just get this straight. Black holes have zero size?
Well, we don't actually know. I mean, one of the reasons that Einstein did not like black holes was because he spent a decade sweating blood and tears trying to come up with a theory of gravity, which obviously supplanted Newton's. And he presented that in a series of 4 lectures in November 1915 at the height of the First World War in Berlin. Within a couple of weeks, a guy on the Alsace front actually fighting, Karl sent him a letter. And in the letter, he had what we call the solution of Einstein's equation.
And this is in your first chapter called An Impossible Thing Before Breakfast. And it was, you write that story so beautifully of this genius who died. But so he gave Einstein an exact solution, which Einstein thought was not possible. Yeah. Can you just sort of explain it to our beloved audience?
Yeah, so basically Newton's theory of gravity has a single formula to describe gravity, but Einstein's has 10. So immediately you see it's more complicated. And what Einstein discovered is that gravity is actually the curvature of space-time. Now, we can't actually see it because space-time is a 4-dimensional thing. That's why it took the genius of Einstein to think of it. So if you imagine Newton thought that the Earth was effectively tied to the sun by an invisible tether, the force of gravity. And that kept it trapped in orbit. And basically Einstein realised this was incorrect. What actually a mass like the sun does is it warps the space-time around it. It creates a valley in the space-time. You can't see it, but the Earth kind of goes around the upper reaches of this valley, rather like a roulette ball, in a roulette wheel. So in order to what you need to do with this theory is you need to find the curvature of space-time, because that is gravity, for any mass. And it turns out that Karl Schwarzschild, who was 40, there was no reason for him, there's no real reason for him to have actually volunteered for the German army.
He volunteered, didn't he? And he shouldn't have, because he had so much to give in his brain and he died.
Well, anti-Semitism was on the rise. He was the director of the Berlin Observatory, and he thought if he signed up, he would show that a Jewish person could be a loyal German.
Yeah.
And he ended up anyway. He went on leave in November, and he attended one of the lectures on the 18th of November that Einstein
You
gave.
describe that so beautifully, how he takes notes of every symbol that Einstein put on the board.
Yeah, and he went back to the front, and within a few weeks, he'd found something which Einstein thought was impossible. Remember, Einstein knew he'd replaced Newton's one formula with 10. Mm-hmm. So he thought actually finding the curvature of space-time, gravity, for any realistic body was impossible. So suddenly he gets this letter from the front. By the way, Alsace was the only bit of the mountains on the western front, from this guy who's found a solution, he thought was impossible, for a compact mass. But Schwarzschild hadn't finished. He realised that this valley of space-time that he had a formula describing would get deeper and deeper if the mass became more and more concentrated, and eventually it would become a bottomless pit that light could not climb out of, a black hole. The prediction is that if a star shrunk at the end of its life, ran out of fuel, shrunk down, gravity would get more and more intense, this valley would get steeper and steeper and steeper, and the collapse would go on forever, as you were just saying, down to an absolute point, which we call a singularity. Now, a singularity is when everything kind of skyrockets to infinity, temperature, density, the whole lot. And what it tells you is that your theory is wrong.
If you've got a singularity, it's like dividing by zero.
Exactly.
Something's wrong.
The theory has been stretched beyond the point where it's got anything sensible to say.
Yeah.
Okay, so of course Einstein, he spent 10 years trying to get this theory, and then a guy from the Western Front has shown him that his theory blows up within a few weeks of him actually presenting it. So you can understand why he didn't like the idea. But he presented Schwarzschild's ideas at the Prussian Academy of Sciences. As you rightly say, at the same time that Schwarzschild was finding this solution, he got these blisters in his mouth, spread all over his body, all over his torso, bleeding, weeping blisters. And it was quite a time before he was in a field hospital he was diagnosed with pemphigus vulgaris. And this is a condition that Eastern European Jews get.
Like the Ashkenazi Jews.
It's when the immune system attacks the skin. Mm-hmm. Now, of course, the skin is a barrier against pathogens. It's also how you regulate heat. So he knew he was going to die. And in May 1916, he went back to Berlin and he died in hospital. I know.
Oh, waste, but his name is immortalised in the Schwarzschild limit.
The actual object, we think a star runs out of fuel at the end of its life, and it's the heat generated by that fuel that pushes backwards and stops the star collapsing. But when it runs out of fuel, it begins to run away, collapse. Mm-hmm. And that collapse keeps going on forever until we get down to a singularity. We know a singularity isn't a real thing. There must be another theory, we think it's quantum gravity, that will tell us that there's something else other than the singularity. It can't be a singularity, it's got to be something. But the actual star is gone. But it leaves behind this kind of imprint in space-time, this well in space-time, and its characteristic size is the Schwarzschild radius,
So that's the event horizon size?
Exactly.
Okay, so it's not the object, it's the event horizon where the escape velocity needed is equal to the speed of light.
Exactly. Correctly pointed out, for something the size of the sun, it's 6 kilometres across. Uh-huh. The Earth would if the Earth could become a black hole, would be about the size of a dry roast peanut. So relatively small. And as some physicists have pointed out, black holes are the simplest objects in the whole of science because they are fabricated from nothing but space and time. That's all they are made of.
Simple in the sense of we can't control them, we can't make them, and we don't know that much about them yet. But at this stage, they have a.
Well, if you take anything around us, I'm looking here at a book we've got here. That's made of countless quadrillion atoms.
Carbon, oxygen, hydrogen, nitrogen.
Amazingly complex.
Yeah.
The black hole is made of nothing but
Space
and time. Nothing at all.
Okay, then
Chandrasekhar.
Chandrasekhar.
Yeah, Subramanian
Somebody
Chandrasekhar.
has told me the correct pronunciation.
No, he's not. He's a 19-year-old.
But he did very well in his maths exam.
He was obviously very talented at maths. And of course,
19.
Because, Einstein, anyone who thought about Schwarzschild's solution thought, well, something's got to stop this shrinkage, because this singularity is a ridiculous thing. Yeah. So there's got to be some other force. And in the 1920s, it looked like there was, because this was the development of quantum theory, our best theory of the microscopic world of atoms and their constituents. And of course, one of the fathers of this was a guy called Wolfgang Pauli, and he came up with the Pauli exclusion principle. Yeah.
So can you just state that for the audience, so about spins and that sort of...
Yeah, so basically the Pauli exclusion principle, it takes a lot to explain it, but in effect, it says that electrons can't sit on top of each other.
They are excluded from occupying the same space.
That's right, and if it wasn't for that, so that is the reason that the world exists, the reason that matter exists, the reason that matter has extent, because you cannot shove two electrons together, because if you do, they kind of resist. So anyone who thought about this thought, oh yes, well, what's going to happen is if a star at the end of its life starts collapsing, eventually the electrons are going to be pushed into each other, but this resistance, because they don't want to be on top of each other, is going to stop the star forming. You'll get a white dwarf. This is a star about the size of the Earth, the mass of the Sun. A sugar cube volume weighs as much as, I don't know, a family car. Yeah. But Chandrasekhar was on the deck of this ship going through the Suez Canal with his quantum books, going to Cambridge.
So he's an Indian person going to a very stratified country.
Yeah, so basically he had written to people at Cambridge, and they'd been quite impressed by him and had actually invited him. But he sat on the deck of this ship going for the Suez Canal. He applies quantum theory to stars, and he realises there's something that everyone's forgotten. It's not enough to apply quantum theory to stars. You have to apply relativity as well.
Because the electrons are moving so fast.
Exactly, yeah. So if you imagine, if you push electrons together, they resist. So they fly around faster and faster. They're like an angry swarm of bees, What everyone had forgotten was that Einstein in 1905 had said nothing can travel faster than light. So this outward pressure of all these electrons, like a swarm of bees, that's what pushes outwards and stops the star collapsing and makes a white dwarf stable. If you get a more and more massive star and they move faster and faster, they can't move faster than the speed of light. So they're kind of handicapped in how much they can push back. And it turns out there's a limit, and it's now known as the Chandrasekhar limit. If the star is more than 1.5 times the mass of the Sun, then the collapse continues.
So in a regular star, you've got the nucleophiles pushing out, gravity pushing in, and when the nucleophiles go out, gravity starts sucking, and if it's more than
1.5 solar masses,
roughly, it'll keep on shrinking past the white dwarf.
Yeah, so the white dwarf is supported by what we call electron degeneracy pressure. So it's not by heat, it's just the fact that the Pauli exclusion principle is making electrons move around. So it continues. The picture has changed a little bit by 1932 with the discovery of the neutron at Cambridge in England. The neutron also obeys the Pauli exclusion principle.
What?
Yeah.
It's got no charge.
But it's got what we call spin. Yeah.
You're kidding.
It has it's called what we call half-integer spin. So if you imagine this collapse continuing past the Chandrasekhar limit, then eventually the electrons and protons in nuclei get jammed together to make neutrons, but the neutrons don't want to be pushed together. They can't be put on top of each other. And you get another stable object which is called a neutron star, and that's about the size of Mount Everest, but it weighs as much as the Sun. So a sugar cube volume weighs as much as the entire human race.
So the first step is a white dwarf roughly the size of the Earth. Yep. If it's a bit heavier, it'll go down to 10, 20 kilometres in diameter, and a little bit more massive than the Sun, 2 or 3.
But it turns out that again, there's a limit. It's not as easy to calculate the limit because the force between nuclear particles like protons or neutrons is more complicated than between electrons. But it's roughly about 2.5 to 3 times the mass of the Sun. If the object is bigger than that, even neutron degeneracy pressure cannot stop the collapse. And so a black hole is unavoidable.
Where do we jump to next? What's the next stage? Is it Einstein and Podolsky, or have we got another step to go?
I think we should simply just say that not many people were interested in this, but somebody was, and that was Robert Oppenheimer.
Oppenheimer?
Yeah, so he was very interested in gravitational collapse and what it would be like, and I won't go into the details, but he, like everyone else, made one big mistake. They thought black holes were black and small. So how would you see a black object that was very small against the blacker space. But if they talked to any astronomers would have said, very rare to find a star on its own. I mean, our sun is a bit unusual in being a solitary star. Most stars are in, pairs, binaries, or 3 or 4. Material can be sucked off the companion star onto the black hole, and as it swirls down like water down a plug hole, it can be heated to millions of degrees. So the story now moves to Australia. Roy Kerr, he's a very interesting person because he grew up in New Zealand in poverty during the 1940s. He was a bit of a mathematical whiz, and he worked in a Christchurch rubber band factory, and he got paid on counting these rubber bands. He realised that if he threw the rubber bands up in the air, they fell in characteristic patterns, and the patterns were related to the number. So he was able to count the rubber bands like 10 times faster than anyone else.
You're kidding.
But he did get a scholarship to Cambridge in England, but he was too young. He was about 16. He took up billiards, boxing, just to use up the time. In fact, he could have gone to Cambridge in England earlier, but he didn't realise. And he eventually ended up in Texas. He finds this solution, which everyone says is impossible.
But he's a mathematician.
For him, it's like everyone says it's impossible. It's like climbing Everest. I'm going to climb Everest without oxygen. I'm going to find this solution. And he actually found it. It describes perfectly every single black hole in the universe because everything's spinning. The institute where he was, a guy had set it up. He needed to put it on the map. So it was decided to have a conference in Dallas. They knew no one would come to a conference on relativity or whatever. They thought quasars had just been discovered, these fantastically bright objects.
We were talking the 60s.
Well, exactly.
And so quasar stood for quasi-stellar object before...
That's right. Martin Schmidt, who was at Caltech.
Oh, he's in another chapter. Which
yeah. He's chapter. So they had this conference. They thought, we'll attract all the astronomers because quasars have been found, and as you just pointed out, these are objects which are, if you take the first one, 3C273, 1,000 times more distant
than... that number. That was 3C means the third Cambridge catalogue.
Yes.
And 2, what was it?
273.
Which amazingly is equal to absolute zero in negative Celsius.
Absolutely right. No, but anyway, he found these things. I mean, one of the key people involved in this discovery was John Bolton, who basically lived in Australia all of his life.
And worked with the Parkes telescope.
What is he?
He's in a different chapter.
He is, and he's probably the only person to have built major observatories in the southern hemisphere and northern hemisphere. So he built Parkes in New South Wales, right. And the Americans realised they were not into radio astronomy after the war. For some reason, only Australia and Britain picked up on it. I don't know why. Thought we need to get into this. We'll get this guy John Bolton, and he set up the Owens Valley Radio Observatory, California. It belongs to Caltech.
So what's it called?
Owens Valley Radio Observatory. So they poached him in about 1956. And then to their dismay, he decided to go back to Australia for the building of Parkes, and he spent the rest of his life there. They thought they'd attract the astronomers. They created a phrase, relativistic astrophysics, which they made up. They entirely made up.
Yeah, okay.
A science without any topic, just to make it a bit sexy. 2 weeks before the conference, Kennedy's shot dead in Dallas, where they're going to have the conference. And nobody wants to come because they think if we go to Dallas, we'll be shot. So they have this conference. Everyone's completely mystified by quasars. They just can't.
Because they were astonishing. What could be so bright?
And Roy Kerr had the answer, and he presented the answer at the same conference, and people talked through his lecture. They read newspapers. What? They completely ignored him.
They ignored him?
Yeah, because they didn't realise the connection.
No, look, just a little diversion here. Whenever on an aeroplane, the cabin crew go through what to do in an emergency thing, I always pay attention. Firstly, because in an emergency, you always drop to your lowest level of training, and I've got no training, and they have. And secondly, professional solidarity with a fellow performer.
A Greek physicist got up afterwards and actually berated everyone and said,
Thank God.
Do you not realise how important this is? The solution to quasars are spinning black holes. Within a year, people realised that these things were pumping out 100 times more light than a typical galaxy, and they fluctuated in brightness, sometimes on timescales of days or weeks.
Which meant they had to be small. That's interesting. They had to be more than the output of a galaxy, but whereas a galaxy is 100,000 light years across maybe, yes. This was like the size of a solar system, exactly. Like about 10, 20 light hours max.
Exactly.
Yeah.
Independently, a lot of physicists realised there's only one possible power source, and that is matter swirling down onto a black hole, being heated to millions of degrees. So this disk of material radiates
on the equator.
Yeah, but not a black hole of a few times the mass of the sun, a black hole of millions or even tens of billions of times the mass of the sun, a supermassive black hole. So that was the power source.
And that was realised what it should be in the 1960s.
Yes, took a long time to confirm that, but it was obvious that was the only source because you can get a lot more energy out, but from friction as the material, because at different distances from the black hole, it orbits at different speeds, just like the Mercury nearer the sun orbits faster than Neptune further away.
Pluto,
exactly, yeah.
So one thing we should point out, the black hole itself is not radiating out of the singularity, but rather the stuff that's falling in outside the event horizon, and it has not yet crossed the event horizon, is running to other stuff also outside the event horizon, and somehow you get a jet going north and south.
In the 1950s, radio astronomers were looking... Well, first of all, after the Second World War, radar engineers thought, we'll try and be astronomers, both in Australia and in Britain. Problem with radio waves is they're 1 million times bigger than optical waves, which means that the vision is 1 million times blurrier. Yeah. So it was a real problem. If you build a radio dish more than about 100 metres across, it collapses under its own weight. So you need multiple dishes. So it took a long while to do this. But in the 1950s, they were beginning to see that the radio emission came from 2 giant lobes on either side of the galaxy.
Either side of the galaxy.
So,
like out of the north and south poles of the spinning.
Yes,
now hang on.
Yes.
Okay.
But it took until 1983 in the Very Large Array, which is in Socorro, New Mexico, 27 dishes are in the desert there. And for the first time, you got an image showing these thread-thin jets of material, oppositely directed jets, coming out and creating these lobes. So if you imagine water from a hose hitting a brick wall and splashing back, that's exactly what's happening. The jets coming out, hitting the intergalactic medium, and the material splashing back and creating these 2 lobes. So these jets are tremendously important because the black holes themselves are very, very tiny. So compared to maybe Sydney, a supermassive black hole compared to its parent galaxy is like a bacterium compared to Sydney. Okay, so you wouldn't expect a bacterium to control the street plan of Sydney, but these supermassive black holes do control their galaxies, and they do it because size doesn't matter. It's the energy they liberate, and that energy is projected outwards, often along these jets. And as you just say, so these jets can go way beyond the galaxy, millions of light years.
Bigger than a galaxy?
What you're just pointing out is that in the last couple of weeks, a survey called LOFAR has actually discovered jets which are about 140 times the diameter of the parent galaxy. And this galaxy...
You're talking millions of light years?
Tens of millions.
Tens of millions of light
and
years
we are
from
seeing
something that has 0 size.
Pretty much tiny little things. So I think if I can just tell you that if you walk past a house and a slate falls on your head, it hurts. And what's actually happened is gravitational potential energy, the energy the slate had by virtue of being high up, has been converted into energy of motion because it's got lower down and eventually giving you a headache. Well, if you can imagine something that's a supermassive black hole that's tens of billions times the mass of the sun, it's like countless quadrillion slates coming together. And the energy liberated is 1,000 times more than is necessary to blow all the stars in the galaxy to infinity. So all you need to do is only a tiny fraction of this energy needs to be available, and it can disrupt the galaxy. So these things can snuff out star formation because these jets can push away the gas, which is the raw material of star formation. So they can control their galaxies.
Okay, now, not even halfway through your book called A Crack in Everything. This has been me with Marcus Chown. And how can people find you before we pick you up in part 2?
I do have a website, and it's at www.marcuschown.com. So it's marcuschown.com. And I'm a bit of a Twitter fiend. I suppose you call that X these days. So you can find me at Marcus Chown.
Okay. And so thank you very much, Dr. Marcus, and we'll pick you up in part 2 coming up shortly. Shirtloads of Science is washed, spun and aired by the University of Sydney.